Okay. So you can check all your answers later, but for now we'll go over the ones that Ethan struggled with, assuming that maybe you struggle on some of those too.
Probably.
Okay. So what's one of them, Ethan?
Number 4.
Okay. So number 4, Nick, was 1 over 504. Did you get that one correct?
I don't know. I didn't. What happened was, I was like, I remembered this morning that I had to do them, and so like, I was in a rush.
Okay.
And so I wrote down all the things. I just didn't get to multiply it all out.
Okay.
I was like, I had to get this done, but.
Well.
Okay.
So homework's incomplete, right?
Yeah.
Okay. So that's the answer. So here it says a bag contains 9 tiles, each with a different number from 1 to 9. You choose a tile without looking, put it aside. Choose a second tile without looking, put it aside. Then choose a third tile without looking. Why do they keep saying put it aside? What does that mean?
It's not repeating.
It's not going back in the bag, right?
So what was the answer?
1 over 504.
No.
Okay. What is the probability that you choose tiles with the numbers 1, 2, and 3 in that order? Okay. I see. So the way they have you do this is, so if I'm going to choose all 9 tiles, how many ways can I choose all 9 tiles?
36,000.
You can just tell me how'd you figure that out?
You just multiply them all together.
Multiply them all together.
9 times 8 times 7 times 6 times 5.
And what do we call that? How do you write it?
The exclamation mark.
Which is what?
Factorial.
Yes, 9 factorial. So we say 9 factorial would be counting every single way to pull tiles out, right? And then, but we overcounted, right? Because what situations did we count there that we did not want to count? We're trying to get to where we pull out 1, then 2, then 3. So
you would,
So this is every single way. If I pulled all 9 tiles one at a time, this is the number of ways I could pull all 9 of them out. Okay? I overcounted by all the times that 1, 2, and 3 are not the first 3. Okay? Regardless of what order 1, 2, and 3 come out. So if I divide by that will get rid of the overcounting. So this is 9p3. Okay? So that equals 9 factorial over 6 factorial, which equals 9 times 8 times 7. Okay? So this is all the ways, this is actually just all the ways you can choose 3 among any of the 9. Okay? This is the way you can choose 3. So what we did was we counted all the ways, and then we don't care about what happens in the last 6, so we divided out all the ways those 6 can be arranged. Okay? So this is just all the ways you can pick out 3. It's 9 times 8 times 7. So is this all possible outcomes, or is this just favorable outcomes? All possible outcomes. Because what we're looking for is, I want the probability that I select tile number 1, then tile number 2, then tile number 3. This is all the ways to select. This is all the ways to select 3 tiles from among 9 in a particular order. So it's 1, 2, 3, 1, 3, 2, Roll. 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 2, 6, 1, 2, 7, 1, 2, 8, 1, 2, 9. 1, 3, 2, 1, 3, 4, 1, 3, 5, 1, 3, 6, 1, 3, 7, 1, 3, 8, 1, 3, 9, and on and on and on. You have to do that through all of those. Then go 2, 1, 3, 2, 1, 4, 2, right?
Well, it doesn't say choose the numbers 1, 2, 3 in that order.
Right, that's what we're trying to do.
Oh.
I'm showing this is counting every possible way you could select 3 tiles from among 9 in order. Okay. Now, if I'm going to select, I want to count the number of ways that I can select tile 1, then select tile 2, then select tile 3. Okay? If I'm going to do that, how many options do I have for what I pull first?
1.
1. It has to be tile 1. Then how many options do I have for tile 2? 1. It has to be tile 2. Then how many options do I have for the third pull? 1. It has to be tile 3. So 1 times 1 times 1 is 1 option. There's only one way that I can select tile 1, then tile 2, then tile 3. So that's favorable outcomes over all possible outcomes, which apparently this is 504. Cool? So this right here, this formula, is what we used in yesterday's lesson, and that unlocks the sample space, all possible outcomes. Cool? What did you have? Or what did you guys try?
I had 504 on top and then like 362,000 on the bottom.
All right, so what you did was you found the probability, you just took how many ways can I select 3 from among how many ways can 9 be selected? That's what it sounds like.
Yeah, I did the same thing.
Okay. Cool. Probably because that's what you had been doing in previous exercises, right? You just try to make it like some other exercises. Okay. But notice this. So your previous understanding of this is another way to think about this problem. Okay. If I'm on that first pull, what's the probability of selecting tile 1?
1 out of 9.
1 out of 9. And then what's the probability of selecting 2 on the second pull? 1 out of 8. And then 3 on the third pull?
1 out of 7.
Notice this is the exact same result we just achieved, right? Because this equals 1 over 9 times 8 times 7. So I think these calculations are related. It's different ways to get to the same answer. So I'm not upset about this solution if this is how you get there. So if you can think through the problem and realize this is how to do it, that's fine. When I first read that problem, this is how I would do it. Okay? And, each of these solutions is a proof for the other, sort of. Cool? Cool. What's another one?
We could do 5. I think 5's the same, except instead of
Yes, but there's more than one option. There's more than one favorable outcome.
They can be in any order, so there's 6 outcomes. So when we just do the same thing, except on the top instead of 1, we'd have 3 times 2 times 1
Mm-hmm.
be 6.
Yes. Okay. So you got number 5 right, though, huh, Ethan?
Yeah.
Cool. Probably because there was an example like that? Yeah. What's another one further down? Further along? $15?
8, 15.
So let's look at 15. Well, 8's pretty straightforward. It's just like the Arkansas and Mississippi problems, right? So how many letters are there? 8 letters. And what are the repeats?
E.
Repeated how many times?
3.
3. So it's 8 factorial is the total number of ways I can arrange those letters. But I have to divide out the overcounting I did by how many ways the e's can be arranged. So how many ways can 3 e's be arranged?
6.
3 factorial, right? So it's 8 factorial divided by 3 factorial. So if you got that, but your number was incorrect, then it's just a computational error. 15. There are 4 female and 4 male kittens sleeping together in a row. Assuming that the arrangement is a random arrangement, what is the probability that all the female kittens are together and all the male kittens are together? Okay. So what they're saying is, if I need all 4 male kittens together and all 4 female kittens together. So for instance, M, 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 F, 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 F is okay, favorable outcome. However, F, F, M, 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 F, F, not a favorable outcome. Okay? Why is that not a favorable outcome?
Because females are split up.
Yes. So we need females and males each to all be together. So how many things am I ordering really?
Isn't there just...
If all 4 males have to be together and all 4 females have to be together, how many things do I really have to put in order? 2 things. You see what I mean? Okay. So essentially we have an 8-letter word with M repeating 4 times and F repeating 4 times. Okay? So how many total ways are there to arrange them then? Yes. Yeah. And we can see that when we realize that thing. We can also do it by saying 8 factorial divided by 4 factorial, 4 factorial. Okay? Then how many ways are there to arrange them total?
So, not mattering if they're split up or not?
Right.
Okay, it would just be 8 factorial.
That's what I thought. But they're doing something funny. It says 70.
Doesn't seem to make sense.
No, it doesn't. Oh no, 8 factorial is 4 factorial over 4 factorial. So look, how many ways can I arrange all the cats? Ready? How many ways can I arrange all the cats? So I have an 8-letter word with 4 M's and 4 F's.
Oh, yeah.
So if it's 8 letters, that's 8 factorial ways. But apparently the males and females are indistinguishable. So I go divided by 4 factorial, 4 factorial to account for M being repeated 4 times and for F being repeated 4 times. This right here is 70. Okay? Because we go 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 times 4 times 3 times 2 times 1. So this cancels. The 4 and the 2 cancel with the 8, and the 3 makes the 6 of 2. So I have 7 times 5 is 35, times 2 is 70. So that's the total ways I can arrange all those cats, which includes like MF, 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 right? Or FM, 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 FM. Those are included in there. So are the 2 ways that we like, where it's all M's and all F's, or all F's and all M's. Okay? So now we have 2 over 70 as our probability, which is 1 over 35. Cool? So really, the permutations are a way to shorten your counting. It's the fundamental counting principle, right? So we're still, when we're doing probability, we're still just counting all the possible outcomes, counting all the favorable outcomes, and then setting it up as a fraction. We're using permutations to shortcut the counting process. Cool? Okay, so let's talk about combinations. So 19.3.
Combinations, the order does matter? Is that what it is?
No, combinations order does not matter. And really, again, in permutations, order matters. Really, that doesn't mean things have to be in an order. It just means they have to have distinct positions.
Yeah.
So, like, if you're selecting a meal, you need to select a drink, a sandwich, and a side. Order matters there. It's just that order is, drink, position, drink, entree, side. Combination. Order does not matter. So an example they give here is like a restaurant has 8 appetizers and they offer a sampler where you pick any 3 and they're served on one plate. So how many ways can you make a sampler, right?
Yeah.
Choosing any 3 from among 8, and order doesn't matter. They're all going on the same plate. So what they're doing here is building the new formula. So it goes, find the number of appetizer samples that are possible if the order of selection does matter. This is the number of permutations of 8 objects taken 3 at a time. So 8p3, how do you do 8p3? Fill them in those boxes. How do you do 8p3?
8 factorial on the top.
Mm-hmm.
8 minus 3 factorial on the bottom.
Perfect. Which is 8 factorial over 5 factorial, which is 336. Now, once I have 3 appetizers, how many ways can they be ordered? Once I have the 3 selected, because my permutation accounts for their ordering, I need to figure out how to undo accounting for their ordering, right? So on part B, it's saying find the number of different ways to select a particular group of appetizers. This is the number of permutations of 3 objects. So we're saying once we have those 3 things, so we selected nachos, potato skins, and guacamole dip. How many ways did those get ordered in my original counting? Right? So what is it? There it says 3p3.
B9.
Yeah, 3p.
Oh, 6.
6. 3 times 2 times 1, right? So we're just ordering 3 objects. So that's part B. So what we're saying is we counted all the ways to take 8 objects and pick 3 in order. So we counted nachos, potato skins, guacamole dip, and potato skins, nachos, guacamole dip, and guacamole dip, nachos, potato skins. We counted all of those, even though we only wanted to know when the 3 got grouped. So basically, for every option we were looking for, right? If we're looking for a group of 3 and order does not matter, how many times did we count each group of 3? So look, I had nachos, potato skins, and guacamole dip, right? How many ways can those 3 be arranged? 6 ways, okay? Once I arranged them one way, should I have been done? Once I had those 3 selected, in any order, I had already identified one combination possibility, one sampler possibility, right? But I kept counting it how many more times? 5 more times. You see what I'm saying?
Yeah.
So for every sampler, I counted actually 6 times because I counted in every possible order when I used a permutation. You understand what I'm saying? So once I counted nachos, potato skins, guacamole dip, I should have stopped counting those 3 things. But I kept counting them because I counted potato skins, nachos, guacamole dip, nachos, guacamole dip, potato skins, guacamole dip, nachos, guacamole dip, potato skins, nachos. Right? I counted it 6 times. Should have only counted it once. So that's what part B helped us do, is identify by what factor we overcounted. Okay? So to find now on 974C, turn the page. To find the number of possible appetizer samplers, if the order of selection does not matter, divide the answer to part A by the answer to part B. Because look, every time I grouped 3 items, I ordered them 6 ways. But order didn't matter. So once I grouped 3 items, I should have been done. So I take that permutation, and I go, okay, how many ways can I order 3 things from among 8 things? Put them in order, not just order them off the menu, but put them in order. Well, it's 8P3. But when I do 8P3, I'm counting too many, not just by a certain number, but by a factor of 6. So my answer has actually now been multiplied by 6. I need to divide by 6 to get the answer I'm looking for, which is 3 factorial. So the number of appetizer samplers that can be created is 336 divided by 6, which is 56. So that should be in the boxes on the top of page 974. Okay, are you on page 974?
Yeah, say it again.
So the 2 answers we got, 336 on the top, 6 on the bottom, equals 56. So this is where we get our new formula, okay? So combinations NCR. So just so we remember, NPR is n factorial over n minus r factorial, okay? Combinations, if order does not matter, NCR is n factorial over r factorial times n minus r factorial. Okay? So notice all we're doing is taking the permutations formula and additionally dividing by how many ways in this case those 3 items can get ordered. So the number of items I'm selecting, I'm taking that number factorial on the bottom, dividing into my permutation to undo my overcounting. Does that make sense? So like in that case, I had the eight appetizer items. I wanted to select 3. All right, well the easiest way for me to figure that out is to do a permutation and put them in order. But when I put them in order, I'm overcounting how many combinations. So I need to divide by what I overcounted by. Okay? Cool. I will say some of these we're using these formulas and it's making the problem a little more complicated, but let's do it anyway, okay? Like for instance, number 4 on page 975, under your turn. A coin is tossed 4 times. What is the probability of getting exactly 3 heads? So, how many things are we choosing from?
4.
2 things, heads or tails, right? So how many ways can these 4 tosses actually come out?
2 ways.
Well, there's 4 tosses. So the first one could go how many ways?
2.
And the second one?
2.
Third one?
2.
Fourth one?
2.
So how many ways?
8. Wait. 1. 4. Oh my god.
16.
16. You multiply, right? So it's exactly what we've been doing, fundamental counting principle. I've got 4 slots. 4 slots is each coin flip. How many ways can the first one come out? 2, second one 2, third one 2, fourth one 2. Okay? Equals 16. That's the total possible outcomes. Total possible outcomes of how many ways a coin can be flipped 4 times successively. So event A, the favorable outcomes, consists of combinations of 3 heads taken from the set of 4 coin flips. So I now have all of these outcomes. I have tails, 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 heads, 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 tails, tails, heads, heads, tails, 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 heads. Okay? And then I have, so like, yes, I just have all these possible outcomes. I'm trying to figure out how many of them have 3 heads in them. Okay? So it consists of combinations of 3 heads taken from the set of 4 coin flips. So what we're talking about is, it's a situation in where we have H, 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 T. How many ways can those be arranged? We know this from the last lesson. This is a word like Arkansas or Mississippi or envelope.
You got. Oh.
Would it be 4 factorial over 3 factorial?
Yes. So what's that?
4.
4. Okay. So there are 4 ways to have 3 heads. So that means the probability is 4 favorable outcomes over 16 possible outcomes, 1/4. What's the probability? Cool.
Where was this from? I didn't hear you say it was
975, page 975.
Okay, I see.
So notice, like, the hardest part of this problem, of these kinds of problems, I think, tell me if I'm wrong, is identifying how to calculate a favorable outcome, right? Like, to think through it and go, okay, so I want 3 heads in any order. That means I need to arrange H, 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 T, right? Okay. Let's look at number 5 on page 975, below the one we just did. On page 975, where it says 5, and then there's a paragraph after it, and then there's some space underneath. You cool where it's located? You just turned the page. You were on it already. Right here.
Okay.
All right. A standard deck of cards is divided in half with the red cards, diamonds and hearts, separated from the black cards, spades and clubs. 4 cards are randomly chosen from the red half. Is the probability they are all diamonds? I'm assuming it should be, what is the probability they are all diamonds?
Mine says what?
Oh, it does? Mine just says, is the probability they're all diamonds?
Mine says is. I got all the typos in my book.
Oh yeah, theirs was the one that said cards and then balls, and the same one is.
All right. So we spoke the other day about how many cards were in a deck of cards. Does anyone remember?
52.
52. So what's half of that?
26.
26. Because look, it said a standard deck of cards is divided in half. So we're only worried about the red cards now. Okay? So 26 cards. So how many of those do you think will be diamonds, and how many do you think will be hearts?
Half and half.
Right.
Half of that.
13.
Yeah, 13 and 13. Okay? So if 4 cards are randomly drawn from the red half, how many ways can that happen? If we only care about whether they're hearts or diamonds. Okay?
Okay.
So how many cards are we choosing from?
26.
Okay, 26.
Wouldn't it be 26 over 13 factorial? 13 factorial.
Hold on. That would be if we're trying to figure out how all of 26 can be ordered. How many cards are we choosing?
4.
4.
Oh, yes. Dude.
Does order matter? No. We're just trying. It's just about how many, not what order they come in. So you guys calculate that for me.
Okay.
Like 14,950.
We're letting you finish.
Okay. Wait. I feel like you did it wrong.
What'd you come up with?
Well, I haven't finished it yet. I have to write everything in like.
And did you
cross it all
do
out.
this into this formula?
Well, yeah, I'm gonna write everything out. I'm gonna write 26 times 25 times 24 times
Okay.
for like forever, and then I'm doing that.
Well, but notice what happens when you do this always.
Oh, yeah, they cancel out.
Right. So if I have 26 minus 4, what's that?
20. Right, what was it? 22.
22. So everything from 22 down is going to cancel out.
Yeah.
So I just need 26 times 25 times 24 times 23.
On the top.
Divided by 4 factorial.
That's fine. I'll erase it.
Well, what do you mean? Erase what?
Oh,
You wrote out lots of stuff. That's cool.
Yeah.
I mean, that's fine.
That was taking me a while.
Yeah, okay. All right. What did you do? Okay. Cool. So let's move on. So that is 14,950. Okay. Now we need to figure out. That's just all the ways that we can select 4 cards from among 26 cards if order does not matter.
Yeah.
So now we're looking for how many of those ways did we just and how many of those did we just select for diamonds, right? So how many diamonds are there to choose from?
13.
Say it again.
13.
13. And how many are we choosing?
4.
4. So this is how many ways you can select 4 diamonds, is this. So now you have another chance to do this, Nick.
Okay. So what was the number that we got from doing the 13 combination 4?
The 26 combination 4
Mm-hmm.
was 14,950.
And we're trying to figure out what's the probability of if we picked 4, how many diamonds would we get?
Right.
So we're doing that. Okay.
So, because this is the number of ways you can select 4 diamonds.
Yeah. Is it 715?
What?
715.
It is 715. So now we have how many ways we can select a diamond, or how many ways we can select 4 diamonds, and we have how many ways we can select 4 cards from among 26. So what's our probability of selecting 4 diamonds?
11 over 230.
Perfect. See, 715 over 14,950 reduces to 11 over 230. Cool. So let's do one more of these where it involves addition as well. So not page 977. So let's look at, there are equally many boys and girls in the senior class. If 5 seniors are randomly selected to form the student council, what is the probability the council will contain at least 3 girls? So if the council needs to contain at least 3 girls, how many girls can it contain?
More than 3.
Which would be what?
Greater than or equal to 3.
Give me a number.
5.
Could contain 5?
4.
4,
3.
and 3.
2.
No.
Oh.
So we're looking for how many ways can the council have 5 girls, 4 girls, or 3 girls? Okay. We want to select all of those. So if we're talking in set language, it's where there is set F for when there's 5, or set A for when there's 5, set B for when there's 4, set C for when there's 3. It's like the overlap of all of those. So it's a union. It's not the overlap. It's the combination of. It's the union of those sets. We're taking those sets and adding them up. Okay. So the number of outcomes in the sample space S can be found by using the fundamental counting principle, since each selection is either a boy or a girl. So we have a 5-person council. 1, 2, 3, 4, 5. Okay. How many selections do we have for the first slot?
2.
For the second?
2.
Third?
2.
Fourth?
2.
Fifth?
2.
Cool. So there's 32 ways that the council can be made up. Okay? Yeah. Now we're going to find how many ways can there be 3 girls, 4 girls, or 5 girls? Okay? So now we're from among 5C3. I'm trying to explain how a council of 5 people having 3 girls on it is 5C3. I'm trying to explain how that would be. So essentially, I now have 5 people, okay? And I want to count how many ways can this council have 3 girls on it. So I'm going to select 3 of these people to be girls. I'm going to let the other 2 be boys. Okay? So how many things am I selecting from?
32.
No, right here.
2.
5. This is the way I'm thinking of it, to explain why it's 5C3. Because what I'm saying is, I now have, we now know that there's 32 committees, right? We're trying to figure out how many of them have at least 3 girls on them. Okay? So I've got this committee of 5 people, and I'm deciding I need to figure out how many of those councils that are possible have 3 girls on them in any order. Okay? So it can be this girl, this girl, this girl, or this one, this one, this one, whatever. How many of them? Doesn't matter. So it doesn't matter order. So I have 5 people. I need to select 3 of them to be girls. Right? So that's 5C3. I also need to select how many of them to be girls? 4. So that's 5C4. Then I also need to select how many of them to be girls?
5.
Yes. 5C5. So if I take all the way, like all the combinations where there's 3 girls, all the combinations where there are 4 girls, and all the combinations where there's 5 girls, then I will have counted all the ways that there's at least 3 girls. Okay? So calculate these. So this is our sample space. This is all possible outcomes. How many 5-person committees there can be. This is our favorable outcomes.
Must be 1.
So just cancel these out. Is that right?
For what?
For all 3 of those, I just like kind of combine all of them.
Well, you don't want to do that.
No. Okay.
Because we're not multiplying them, see?
Okay.
We're adding them up. Because remember, we're counting. So that's why we did them separately. If there was a way to multiply them all, there'd be another formula for it.
Okay. last one, would it have 0 over 5 times 4 times 3 times 2 times 1?
So it's 5 factorial is the n over r is also 5, so 5 factorial times 5 minus 5 factorial. So that's 0 factorial, which is 1. And we have 5 factorial over 5 factorial, which those cancel to leave 1.
The last one?
5c5.
Yeah.
Because listen, here's what we're talking about. How many ways can I group without, when order doesn't matter, 5 things if I'm selecting 5 things?
How many ways can I group 5 things on?
So look, I have 5 people. In this class, usually there's 4 students and a teacher.
Yeah.
Let's say order doesn't matter. There's no teacher. We're all just people. We're making a committee.
Okay.
5 people. How many ways can I make a 5-person committee if those 5 people are my entire pool?
1 way.
1 way. That's what 5c5 is saying.
Okay.
And notice on 5c4, ready? I have 5 people. How many ways can I make a 4-person committee? Well, look at this. How many people am I leaving out when I do a 4-person committee from among 5?
1.
1. How many ways can I leave 1 person out?
1 way.
5. I can leave out Ethan, I can leave out Kennedy, I can leave out Nick, I can leave out David, I can leave out me. So that's 5 ways to make a 4-person committee. Cool.
Yeah. So, and then the first one, just, we left with, 10 over 3, wouldn't you? I don't know.
I'm thinking. No, it should be 5 times 4 times 3 over 3 times 2 times 1. Because, and this is why it's helpful to write it out. At least write out this step. 5 factorial over 3 factorial times 5 minus 3 is 2 factorial.
Yeah, that's good.
So that just cancels the 2 and the 1. I have 5 times 4 times 3 on the top. And then 3 times 2 times 1 on the bottom.
Yeah.
Cool, so we had 10, 5, and 1, right? So that's 16. Yeah. Cool. So we're about to go on to the next lesson. We'll do 1 to 10. Page 978 to 980.
So you're going to 19.4.
Mm-hmm. See, it's kind of odd we didn't do this with Pascal's triangle when we were doing combinations before. And there it is. Ridiculous. So
Is 19.4 the last section?
in this module.
Yeah.
So we're going to take the quiz on Monday. Originally I wanted to do a take-home quiz over the weekend, but now we're in a position where David and Kennedy are missing these 2 lessons, and David has now missed 3 lessons. So they're going to have to watch this video over the weekend, and then we'll hopefully we'll take the quiz on Monday. Okay? Tell them that. All right. So now we're going to talk about kind of how to deal with probability of multiple events. Okay. So we've been dealing with probability of just a single event from unless sample size or whatever. So let's take a look on 985. Okay. So they're talking about so mutually exclusive events are things that can't happen at the same time. You can't have both things happen. So for instance, like things that could both happen is like rolling an even number and rolling a multiple of 4. If I roll a multiple of 4, it's also an even number. That sort of thing can happen. But here we're talking about a 12-sided die. So I roll, there's 12 things that can happen. Okay? 1 through 12. It's saying let A be the event, we're on page 985, there's a Venn diagram, we're going to fill it in. Let A be the event that you roll an even number. Let B be the event that you roll a 7. Okay? So fill in that thing where S is a sample space, so there can be things outside of A and B. But evens go in A, multiples of 7 go in B. You're numbering 1 through 12. Put in the numbers 1 through 12 in that diagram.
So multiples of 7 go in B.
Evens go in A.
Evens go in A, and the rest go in.
So will there be anything that's in both A and B?
Uh,
An even multiple of 7 in 1 through 12?
No.
No. So there should be some things, Ethan, outside of those circles in the sample space. So what numbers are in the sample space outside of A and B?
1, 3, 5, 9, 11.
Okay, what's in A?
2, 4, 6, 8, 10, 12.
And what's in B?
7.
Perfect. Is that what you have? Great. So what's the probability of A? What's P of A? This is part B now. P of A. 6 out of 12. Which equals 1/2. What's P of B?
1/12.
1 out of 12. So now we want to calculate the probability of A or B. Okay? So under D, they're saying what's NS, so the number of elements in the sample space is what? Sample space being the entire universe, not just the ones that are outside of A and B. 12. So N of S is 12. Now, what's the N of A or B? When we have OR, listen up, when we have OR, we add. This makes sense, right? Because how many students in this school are 9th or 10th graders? Well, we would add them all up, right? So N of A or B is N of A plus N of B. So that's what?
7.
Yeah, so 6 plus 1 equals 7. So the probability of A or B is the N of A or B over the N of S equals 7/12. Now notice, under E, that if we had just added the probabilities, added P of A and P of B, it would have been the same thing. It's 1/2 plus 1/12 is 7/12. So So you've got a blank down there where it says P of A plus P of B blank, P of A or B, that's equals. So when we have two mutually exclusive events, meaning there's no overlap in them. You follow me? There is no overlap in them. We can just add their probabilities together if we want an either or. Okay? So, this dice example is probably the easiest example to come up with. But like, even if it was a six-sided die, if event A is evens and event B is multiples of 5. Okay, so you have 2, 4, and 6, and 5. 1 and 3 are not included, right? It's 3 out of 6 or 1 out of 6. I just add those up to get even or a multiple of 5. When they're mutually exclusive. So, but what if they're overlapping? Okay, what if they're overlapping? So now look at this, and let's just talk through this real quick. On 986, it needs to be filled in too. That Venn diagram needs to be filled in too. So we're looking at a dodecahedron again, a 12-sided die, and so now A is the event that's an even still, but now B is the event that the number is greater than 7. Okay? So now we're going to have some overlap. So what evens are greater than 7 in 1 through 12?
10, 12.
So those go in the middle. What odd numbers are greater than 7? 9 and 11 go in just B, not A. Now, what evens are remaining that we haven't named yet? 2, 4, 6. Those go in A, not B. And what numbers are outside of the sample space? Outside of A and B. In the sample space, outside of A and B.
1, 3, 5.
1, 3, 5, and 7.
Oh yeah, because it's greater than 7.
Greater than 7, not equal to 7. So again, we've got 1, 3, 5, and 7 outside the circles, 2, 4, and 6 in just A, 8, 10, and 12 in both A and B, and 9 and 11 in just B. All right. So what is the probability of A?
You get the 12.
Oh, we're on page 987 now. No, because the stuff in the middle is still in A.
Yeah, so it's 6 out of 12.
Right. So P of A is still 1/2. Because it's, remember, A is rolling an even, so there's still a probability of 1/2 of rolling an even. What's the probability of B? What's the probability of rolling a number greater than 7?
12.
5 out of 12. Now, what's the probability of rolling an even greater than 7? So look at D on page 987. D on page 987 at the top says calculate P of A and B. So and means intersection, not union. Intersection, so things that are in both. So how many things are in both?
3.
3. So that's 3 out of 12. That's the probability of rolling an even that is also greater than 7 is 1/4. Okay? So now, using the Venn diagram, we want to find the probability of P of A or B. Okay? So how many things are in A or B?
Two, 4, 6, and 9, and 11.
How many?
5.
8. So you're still not including the overlap. Okay, which is sort of the key. So we're saying if it were an even or greater than 7. So the fact that it's both means it is included. We just want to make sure we don't count it twice.
Oh, so we're counting everything that's in the sheet.
Yeah, whether if it's even or greater than 7. So that's P of A or B. So that's 8 over 12 is 2/3. Now pause and notice this. Remember before, with mutually exclusive events that do not overlap, if I want the probability of one or the other, I can just add up their two probabilities. That's what we just showed in the previous example, right? But here, since they're overlapping, if I were to do that, I would be double counting what's in the middle. So if I took P of A as 1/2 and P of B as 5/12, and I just added them up, I'd be counting all those things in the middle twice as favorable outcomes. You understand what I'm saying?
Yeah.
Because if I said there's 6 things in A and there's 5 things in B, I just counted 8, 10, and 12 twice with the 6 and the 5, right? So I overstated the likelihood if I do it that way. So I need to make sure I don't count the overlap twice. So look here, on F. P of A is 1/2. P of B is 5/12. P of A and B, meaning it's in both, is 1/4. So in order to find the probability of P of A or B when the events are overlapping, is P of A plus P of B minus P of A and B. So 1/2 plus 5/12 minus 1/4 in this case. 1/2 plus 5/12 minus 1/4 equals 2/3. So notice, okay, when I take P of A and I add P of B to it, how many times did I count P of A and B?
Once.
When I take P of A, all of it, and P of B, all of it, how many times on the Venn diagram, look at the Venn diagram, if I take the entire circle of A, and then I add to it the entire circle of B, how many times did I count the overlap? Twice. That's why I subtract out the overlap. See? So what if I were to draw a picture of that little, this is favorable outcomes of A, this is favorable outcomes of B. I counted the leaf twice. I only want to count it once. So I subtract out just the leaf. You see?
Yeah.
And therefore, what I end up with is that. Cool? Everybody happy?
Yeah.
This makes sense, right? So they summed up that rule in a box on the bottom of 987. Okay? So let's look at number 5 on page 989. So we want to look at the probability that they have a headache or they didn't take medicine. Okay? So where is the overlap of those? So listen, probability of a headache or no medicine. So we have an event, kind of watch me for a second. We have an event where somebody has a headache. There's another event where somebody took no medicine. Who are the people who are in both events?
Headache with no medicine.
Person who has a headache and took no medicine. Where on the chart is that?
225 is.
Well, 25 is no headache, no medicine.
Or 15 is.
15, headache, no medicine. So do I care about the 48?
No.
Not really. Other than to help me define my sample space. Right? So I need to know total how many we are. But so what's the probability that somebody had a headache?
27
27 out
out of 100.
of 100. What's the probability that somebody took no medicine? You're
40.
40 out of 100. So what's the probability of headache and no medicine? Not or, but and no medicine.
15 out of 100.
15 out of 100. So now we have our core data. Okay, because look, what we just did was we said headache, no medicine, both. We just identified those probabilities. So what was headache?
27.
What was no meds?
40.
So now we've double counted the people who had a headache and took no medicine. So we counted them twice. So we need to subtract out 1, so only 1 case is left. So minus 15 out of 100. Right? So that's 67 minus 15 is 52. $13 out of 25. Cool. $9.89 to $9.92. Cool.